No audio outside.
Maybe let's start a bit more general, and maybe some of you have considered building a quantum computer. And then basically you have two possibilities. Either you look for synthetic qubits like superconducting qubits, spin qubits, and so forth, or natural, of course they are in green here, natural qubits, atoms and ions or photons. Each of these approaches have their distinct challenges. The synthetic qubits, of course, to make them identical is a non-trivial task, and a lot of energy goes into it. And of course, connecting them is also a challenge. For natural qubits, there is a challenge to position them. You need to hold them. They are identical, that's easy, but you need to somehow hold them. You need to transport them to bring them together, and the connectivity is also a question. How can I connect this with that qubit? And one of the joint challenges is, of course, the scaling challenge. In this first part of the talk, I will talk about the transporting and the connectivity and the scaling challenge. So if you think about transport on a bit larger scale, then for humanity, it was a big step when they figured out how they can transport classical cargo, when they got rid in carrying stuff and then handing it over, next person carrying. So they finally figured out how the wheel works, and nowadays we are rather sophisticated in using wheels. And in a way, we are in a time where we now try to figure out how can we transport quantum cargo. And I would say we're still a bit on the pre-wheel or the first rollers kind of type of stage. So still quite a bit to do. And one also has to say, of course, this didn't happen over 1 or 2 years. It took humanity a big time. We hope we are faster with quantum. And I will tell you about using topological transport to transport quantum states, and in particular to split singlet states in a topological pump and then make them pass through each other and then come back and still having the same state. And I will also would like to address the scaling challenge. Sometimes when you think about, well, maybe in the morning, on Sunday morning, you wake up full of energy and think, how should I build a quantum computer? And then you think, but it was millions of qubits one has to do. And then on the other hand, then one thinks, actually, when you did chemistry, then there you had all these orbitals, and it was fun to put a spin up, spin down electron into an orbital. And well, that's a local, but an entangled state. One needs to be spin up, one needs to be spin down. And you wonder, well, couldn't one use all this entanglement? And if you want to use that, then maybe you could split those two, this state into two, spatially separated, keeping it entangled. But here too, The trick is you need to do it in such a way that when you bring them back, that you still have your singlet state. So that's what you need to do. You need to take it apart and bring it back. And then you could also, well, take it apart, let it interact with another one, and bringing both back. And, well, with electrons, this is very fiddly. I mean, to take an electron out of an orbital and then putting it exactly back in a reversible manner is maybe still tough. So with atoms, it's better to do that. And that's what we do in this topological pump. So we do take it apart, and then we let it pass through each other. There we use a swap gate, and then we bring them together again. So, and we let matter and light work together. And on a bit more general scale, well, that of course was a very early, that's, I think, probably for the standing waves, the first work where the idea was mentioned that you can put atoms into a standing wave and they are polarizable objects, so you can trap them and hold them. Of course, you can expand this idea in 2 and 3 dimensions, and here it's also, of course, nice to show these pictures when a BC expands. But here I would like to emphasize one point that we understood here in Munich kind of early, that if you control the time phase between those 2 lasers, you can get interference pattern where you have a lambda periodicity in this direction. Or if you change to 90-degree time phase, you have a periodicity of lambda half. And I will come back to these 2 possibilities, because the way we construct this topological pump is that we control this long wavelength interference pattern with respect to the short wavelength. But they are both at the same wavelength, but same laser frequency, almost same. But in one direction, they are just half or full periodicity. And of course, one can now imagine you have this lattice structure, and you want to have a lot of these pairs, kind of like the paired electrons in orbitals. And for that, we use quantum degenerate Fermi gas that we put into a 3D optical lattice. And as well, it's like bringing coals to Newcastle, as you know, that fermions in a standing wave lattice, you can look at it in terms of Hubbard model. So the atoms, in our case, we have a spin up and a spin down encoded in different magnetic sublevels, and they can tunnel on this lattice. And if they both tunnel on the same side, they interact, and this interaction one can tune with a Feschbach resonance. That was meant to come here, this Feschbach resonance. And one can also measure whether one has 2 atoms on a side by encoding the interaction. Once they interact, they have a slightly shifted energy, and you can address them with a radio frequency and move them into a 3rd state, and then you can measure that spectroscopically. Okay, that's how the lab looks like. It's an insider view because we don't have our curtains around it, so it's not a 2 black boxes which then look immediately like quantum computers. Reality is this one. And that's the team. Conrad Fiban is the leading postdoc. And you see also some former members here. Kilian is probably sitting here, and Anne-Sophie Walter did once a thesis in in Emmanuel's group, and I think Joachim was also at MPQ at some point. Konrad also, yes. So you see, wonderful exchange. So let's look at the singlet pairs in the lattice. So if we kind of can prepare them a bit random, they are not exactly one per side, but they are filling up. And let's look at one singlet pair first. And now we can, by controlling these two lattices, we can prepare a kind of a double well structure, and we can control the interactions. So we prepare with attractive interactions, and then we move to repulsive interactions and bring the second lattice down. And what we leave, if we do that adiabatically, then what we leave, what we have then finally is a state where there is an atom on the left side and one on the right side, but we don't know which spin is where. So it's a kind of like a correlated Bell state. And what our challenge will be to take that state apart. Well, here it's again. And for that, we use topological pumping. So the main idea of topological pumping is that you have a time and spatially periodic system. And one implementation is that you take a standing wave potential with a short wavelength and one with twice the wavelength. So if you move it, then you have a time and spatially periodic situation. And with this, you can transport insulating states, or also you can look at it in terms of localized states, which are transported by one side per cycle. The parameters of the system is the offset between the lattice sides and the difference of the tunneling between interdimer and between the dimers. And that is plotted here. And as long as you're slow enough, as you're adiabatic and you don't pass through the symmetric point in the center, then you will have this adiabatic pumping. And it's illustrated here also. And there had been early work both in Emmanuel's and Monika's group and in Takahashi's group in Japan. And here is one way how one can look at it. There is a localized state on the dimer, and then you see how in time the other potential moves, and this state evolves into a state which is after half a period, kind of half a side further. And if you continue periodically, it will just move. And well, one may think that it's moving with a long wave potential is maybe not so surprising. A bit more surprising is that the next higher stand, though it's state, so it's made up of two mini bands, which are very low in energy compared to the next higher band. Lowest mini band moves to the right, the next upper mini band moves to the left. So that's important. And that is also topological. I mean, it's also per cycle, it moves by one side. And the trick will later be that we have our state prepared that it's one atom must be in the lower and one atom must be in the upper mini band. And we have two atoms of different spin. You see where it goes. Okay, and the way how we implement our topological pump, that now as to come back to what I showed at the beginning, is we create a lattice with short wavelengths and one with longer wavelength, and that we can move relative to the other. But both are at, in our case, close to 1064 nanometers. So all perturbations are common mode. And there you can see now, well, if you have single out a single line, and you can, of course, to make 1D tubes, and that's what we do, then you have exactly this situation. And you can implement that fairly easily by reducing the back reflection. It was somehow something I think we overlooked in the last 20 years, that one has such a fairly easy way to create such a situation. We stumbled about it in another experiment where we suddenly saw something happening. That was the self-organization experiment. And one implements it, and it works immediately. I think it worked immediately. So now from my perspective from the office, but I see Kilian smiling, but I think that movement worked more or less immediately. You see, these is the lowest miniband, and we had some population, the upper miniband, which moves in the other direction. We also did some quantum simulation experiments with that, but I don't want to go into depth here. A real fun experiment was that there is a point where you reflect this topological pumping because you're in a trap. Your topological, you have a barrier between a topological region and a non-topological region. But this can also be induced by interaction, and then you get a reflection. And actually you get correlated pairs already there. That's where we started then further thinking about things. Now let's first look at, let's assume we have this pair, spin up, spin down, sitting on the lattice sides. And then we just, to both of them, we apply this topological pump. So they are attractive pairs. So they both tunnel one after the other. And there we can easily move by 100 lattice sites. And it actually has a very high fidelity. So it has a 99.5% fidelity per cycle over 50 cycles, over a really large number of cycles. We can do now, let's look at now at the splitting of these pairs and then looking at them. So that's very much related to some work of Emmanuel some time ago, the singlet-triplet oscillation. So we split this, this pair, and then we apply a magnetic field gradient. And a magnetic field gradient, so what you have on this double L, you have a singlet state and a triplet state. So in principle, they form a decoherence-free subspace, but you can break it by a magnetic field gradient. So you can then, by applying a magnetic field gradient, you can induce the singlet-triplet oscillations. And these are shown here. And we again, you go back and then you measure, do you have both on this little side, and then you spectroscopically can determine that. That's how the data was taken. Okay, and now what we do is that we apply this topological pump. And there we take advantage now of the fact that we have on those two sides, we have one spin up, one spin down, exactly one spin up, one spin down. And they occupy the lowest and the next higher miniband. And now we switch on the topological pump, and the consequence is that they are moving apart, but still correlated. And we can then again apply our magnetic field gradient. And now they do kind of very distant singlet-triplet oscillation. And then we can move them back and do the same detection scheme. And applying the same gradient, then we get, of course, much, much higher oscillation as are shown here. And now you might wonder, okay, but there are these many singlets, which we had in one tube, and now we let them move, separate them more and more. At some point, they will collide from one singlet pair. It will collide with another one. So, and then we will not get these nice oscillations. And our first data were not nice oscillations, just many oscillations. But then we thought a bit, and then we figured out what we can do. And what we can do is to do swap operations, to do it in such a way that the speed or the parameters like our tunneling parameters, that while they pass through each other, that they do a swap operation by super exchange, kind of a super exchange swap gate. And then they can pass through each other and they can move on. And then we can do that on the way back, and they are still entangled. So that's why we have this that's why we call it intertwined entanglement. And then they go back. And that's, yeah, depending on how far we go apart, we then can choose where we have, at which frequency do we have our singlet-triplet oscillations. Okay, we have it again. And now I think it should be clear what is meant there. These two still remain entangled and go back. We can also, in general, this can be used as a variable swap gate. So we can also do, for example, a swap squared gate. That means that it's reflected. And this reflection also shows up then in our singlet-triplet oscillation spectrum. The characteristic peaks correspond to that. Okay, so we are quite happy, I must admit, about these results, because it makes one hope that one can connect distant qubits from here to here and pass through other qubits. And then depending on whether you want to connect them or not, you can let them pass through, or you can make them interact in some form. And one option would be to create an end-to-end kind of effective interaction in this digitalized way. But you can also, in a quantum computer, when you want to have this qubit interact with this, should be possible. You can also think about ways where you let them move apart and then do an intermediate measurement, and then know those two are entangled. And there's a lot to play. Of course, we have not done all that, so there's quite a bit still to do. And also a nice aspect is to use it as a magnetic field gradiometer, non-classical, because I mean it's a decoherent-free subspace, and it's only magnetic field sensitive on magnetic field gradients. Okay, so well, I have an empty slide now. So what comes next? Let's have a look. Pair production in optics. So here, Quantum Optics Institute. Okay, in photons, when you prepare photons, well, these parametric down conversion mechanisms is something which is used a lot. And basically you send in pump photons, and then you have this nonlinear crystal, and out comes two photons with energy and momentum conservation on different different spin or different colors, depending on which process you exactly have. And after a certain critical coupling, you get this increase, this over exponential increase of pair production. And to produce cold atom pairs, well, there are the mechanisms of collision. So you have MF equals 0 atoms, and they collide, and then they can produce spin-ups and spin-downs. So that's actually fairly slow process. Then people have used similar techniques to what I will show you for thermal atoms in cavities. And some people used colliding and driven BECs. But I want to obviously focus on what we are doing. And that is using a cavity-enhanced higher order superradiant process. That's how I would describe it. Let's first look at what the setting is. So we have a BEC in between two cavity mirrors and a short pulse and a running wave. 65 microsecond, everything is over. So it's fast. If we can produce pairs within these 65 microseconds, we are much faster than the collision people. Let's first, for simplicity, look at the superradiant process in this setting. I mean, there are one process one can easily imagine happening is that you absorb a photon, a pump photon, and then you dump it into the cavity, and then you should get a correlation between, well, if you scatter a photon for momentum conservation, you need also to have scattered an atom. So that, but here is an extra line, and that is the cavity resonance. So this process, if I am on resonance with the cavity, I can do that. Let's assume I move, well, that's the process I just described, absorption and emission into the cavity. And now let's assume this cavity is off resonant here. But then, of course, you more and more suppress this superradiant process. And then in physics, the question is, yeah, what is the next order process? And if you adjust it in a clever way, then here you have MF sublevels. There is another process where you absorb this photon, which is now the superradiant photon, which is now a virtual photon, and emit it into the pump again. And this is the next higher order process. No cavity photons lost. And this process produces another atom. So these are not each two atoms. It's one atom in a momentum superposition state, and the other atom also in a momentum superposition state. But you produce pairs of these atoms. So it's kind of, that's why, yeah, cavity enhanced higher order superradiant process. I think it covers what it is. And in our experimental setup, with the present possibilities that we have, a lack of laser power is always in quantum optics. we will get a new laser soon. And we can produce 10 pairs before we lose the first photon out of the cavity. So what does that look like? Here is, well, it's in the Y polarized light field, and we use a vectorial coupling of the MF equals 0 states at 790 nanometers, so far off resonant from all atomic transitions. And what we see is indeed that we forward scatter MF plus 1 atoms and backward scatter MF minus 1 atoms. And we also see when we change the number of atoms with this critical behavior after a certain number of atoms, we see this pair production. I mean, let's go back to these nonlinear crystals. And if one teaches this about this pair production, then often teaches also these combs. You produce one of the photons in one comb and another photon in the other comb. And similar, that's here, you have one forward and one backward. And one would say this would be like, well, one comb and there is the other comb, and you produce this pair of atoms. Yet, in these scenarios, the fun point is for photons that you have those intersections where you get your bell pairs out. And that requires a kind of two channels or two possibilities where the particles can come from. And actually, as when I describe you more precisely the mechanism, that we can tune to such a situation. And this is, one can see in this picture. So here we look at two MF equal 2 particles and at the two, this high order superradiant process. So the cavity is detuned either, well, where are the two? Either here or further up. So we can detune the cavity, well, here it's detuned here, or we can move it, say, here. So we can tune the cavity. So we don't want to have it on one of those resonances, because one of these resonance means one of these atoms moves to the MF, say, +1 state. And that would mean one is scattered forward. But we only want that happening if we absorb that photon and scatter the other one in the other direction. But now we can either go via this MF plus intermediate state or via the MF -1 intermediate state. And if we tune our cavity in between, then we can go both ways. So the first one was as the previous situation, and that is when we go in between. Now we can measure the correlations between the upper, the scattered upwards, scattered downwards, and that's plotted in the upper right correlation diagram. And in the other case, here we see correlations between, so these are, in reality, they are separated by Stern-Gerlach, but we can see the correlation. So we take a lot of data. We can see the correlation between those and the correlations between those. Unfortunately, at this point in time, well, at this point in time, maybe our detection number per how many atoms we can detect per shot might be enough to see number squeezing. At that point, we had not the good enough resolution to see number squeezing. We could see the correlations, but not yet the number squeezing. But one can also ask the question, is this process induced by vacuum fluctuations? And that there we could say something. And again, there are those two data sets, and now we take lots of measurements and look at the statistics of the produced pairs. How many pairs do we produce? And we see this characteristic Bose-Einstein distribution with a large variance. And this we can now compare with a calculation, modeling our system with in a truncated Wigner approach, so where quantum fluctuations are taken into account. And there we can place in these calculations, that is, this is experiment, this is a simulation, well, the full line is from above. And there we can now look at, we can artificially put in a seed, which breaks the symmetry and leads then to a distribution in the calculation, which looks very different. So already by 1 photon seed, we see a substantially different distribution. At 5 photon seed, we would expect a much narrower distribution around here. So there you would always kind of seed in one direction and then continuously produce a coherent state. But this is compatible with a seed with negligible photon number. One could speculate in the future, because now we produce these atom pairs in momentum states, so spin momentum correlated states. And there one can wonder, can one do atom interferometry, quantum enhanced atom interferometry? And there's one form of atom interferometry for this type of, I mean, in optics, the people had tried a bit in this direction. And I think for atoms in this spin pair production, there's in Markus Oberthaler's group one paper. And but there it's kind of momentum state, not momentum state states in the trap. So here we would have momentum states, and one could imagine now to separate them and then reverse the process, and then they would be sucked into the MF equals 0 state. And there one can have quantum enhanced interferometry. So we were wondering, is there any hope for that? Because that would need coherence. And we believe that we are very coherent, because if we let this pulse run much longer, then we do see a coherent dynamic where the number of, say, atoms in the MF equals 0 goes down, and then it grows again. And then there is some time evolution. So we are optimistic, but of course, experiments will show us. And this is the cavity team, and Panos is leading this effort, and of course, co-PI is Tobias Donner. And do we have other people from here? I think Fabian Finger, no? He was here. Yeah. Okay, and a beautiful lab, isn't it? Yeah. It's also open here. Do I still have 5 minutes, or? Okay, good. Then, I mean, I talked a lot about pairs, and not photon pairs, but atom pairs. And then one could wonder, if I have these pairs, maybe one can manipulate the pairs somehow. When changing something on one part of the pairs, and that's what we try here. It is the following idea. So you have the lithium here in this case, quantum degenerate lithium gas, strongly interacting, many pairs, very strongly correlated. And now we want to create a dark state which acts only on one of the legs or one of the pairs. Say the one state. Well, this dashed line shows the strong atom-atom interactions, and now one can wonder, can I manipulate this one and create, say, a dark state, and somehow look what's happening to superfluidity or what else? And if you're, of course, not too far off resonant with any excitations, you cannot do that in a total bulk system, because then you heat up if you send your light. So what we do is we have our transport set up, and in a very localized region, so 1 micrometer region, there we play with our pairs. And we will also look at the transport, but first just look what is happening when we have this configuration. Well, here I'll show you how it is, how it functions. So we have this elongated cloud. We send a TM01 mode, and then we have a 2D channel between them. And then we can take another laser beam, and then we have this kind of 1D channel that's here in the middle. And we can also add another laser beam, which with which we control the chemical potential here in this region. And now in the center here, we add another two beams to create this dark state between the 1 and the 5 state. And in the first measurement, we just have these superfluid reservoirs, same chemical potential and temperature, and send in this beam in the center. And then we scan the two-photon resonance. So here's lumbar scheme is shown. And we can nicely observe here in the loss rate plotted as spin up versus spin down, because only on one we act only on one spin. And we can see this characteristic EIT dip. So that seems to work. But now the question is, of course, is something happening with the superfluid character? So basically, what we do there, if we are in the dark state, we admix a bit of this auxiliary state or state 5. So what is usually happening now in the absence of all these dark state beams in this transport configuration is that your delta n over n, so you have an imbalanced potential. Usually, if you have a normal gas, it would just exponentially decay, and at some point you would have the same number of atoms in both reservoirs. If you have a superfluid, what you observe in the case of this 1D channel is you see a very fast decay and then a nonlinear behavior. In terms of curve I over V or resistance curve, then you see this strong nonlinearity. If it was just ohmic, it would be linear. So this fast decay and non-exponential decay, that is a characteristic. And now we add just one of the two legs in the dark state. Okay, so we just add dissipation. If we add a good amount of dissipation, then we see it is getting over into exponential decay. If we do it strong enough, or very weak, it's also okay. So we see this. And now we add this additional beam to create a dark state. And then we see indeed that it seems that these pairs go into the channel, and then this one state, by admixing to the third state, there is some phase rotation of this one state, then it will get invisible to the light, and they both will pass through the light field. I mean, the goal here is we would like to be able to add quite a bit of a phase shift to this state. That would be cool, because then maybe one can prepare kind of P-wave type of states by shifting the phase. Whether we can go so far or not, we do not know yet. But there's something else we observed. We can also measure a transport time scale. So we have these decay curves, and we can say, okay, what's the time scale of our transport? And we can see that if we are on resonance, and now tuning with respect, we tune now this two-photon resonance. So we tune that, and we see that we have the fast transport at that resonance. But what puzzled us was this asymmetry, because the potentials that we induce in the ground state, in this dark state, they are negligible, 4 nanokelvin. And also we saw that the loss rate had a sharp feature, and also the non-interacting didn't show this feature. So we believe that is some interaction feature, but which we do not have a theory for yet. And with this, well, in this experiment, we had quite some theory collaborations with Thierry and Wilhelm and Eugene. And this is a cool lab. There you see a picture of the lab. And with this, I would like to come to an end. So we looked at creating, transporting, and manipulating correlated pairs. And I would like to thank the whole team. And it's a great pleasure to work with each of them. And I would like to thank you very much for your attention.
Hey, thanks so much for the great results and the nice talk. I'm sure there are many questions. Yep, I think probably I have to walk around, or should I turn on the stealing mics? Just turn on the stealing mics.
Doesn't work.
I think it should be fine.
Oh, it should be
on. Yeah, it should be on screen.
Okay.
Maybe, sorry.
Okay. Thanks for your very interesting talk. I wanted to just ask a very nice question about the details. Can you see something like a squeezing or limit cycle or these things in the dynamic of them, or measure, of course?
In the pairs of the cavity.
Yeah, the dynamic of them. Finally, you measure out.
We can. There is one set of measurement that I've not shown you. That is, if we let the pulse be longer, then we see a kind of a depleted pump regime. And then we get anti-correlation. So it either goes into the one state or into the other state. So there is some, what would in optics be depleted pump regime. So that we could see the squeezing, our atom number resolution is, or at least was during the measurements, not good enough. We have improved now, but we will see whether we improved enough. Measuring atom numbers is always.
And also, can you write down something about the dynamic of them and how they are interacting, light matter interaction?
We can. I mean, we can. I showed you this for a longer time. This the dynamic where we go scatter into the state and back, and there are also higher order states where they also go in, and there I think there we have a fairly good numerical understanding for that.
Because for me, it makes some sense that it's like a two magnum Raman scattering. And I was thinking that if you can write the interaction like a nonlinear two magnum Raman scattering and explain with that.
We have our interactions and everything we can write down. It's a typical cavity long range interaction. But one can write it in terms of those interactions. I think the most intuitive process is this high order superradiant process. But you can use the usual cavity description. Well, Helmut Ritsch, for example, developed a lot of that formalism.
Okay, thank you.
Yeah, thanks for the many interesting results. So I have two questions. So on the swap gate, the first part, maybe?
Yeah.
Can you put an estimate on the fidelity of the swap gate, or?
We have measured the swap gate and the fidelity. I think it was in the I think it was in the 70–80% or something. However, we have a solution for that. We are working now with much higher gate fidelities. We in our preliminary, but now I'm online. It looks good. It looks good. We would still like it to look even better than that, but it looks very promising. We are very happy with that.
And in the pair production for the entangled spin, in principle, could you? You showed the correlations, but you didn't show entanglement. Right?
Yes.
So what you could do, maybe.
Yeah.
You could just have to do some local rotations, independent local rotations.
Yes.
pairs.
Yes.
So did you think about that? I mean, if they just separate long enough, then you could just have on one of them.
Yes. Yes.
Show
Yeah.
analysis or just
Yes. Yeah. We will do another round of experiments on that. We had some vacuum issues in between, but we are now improve both our detection in the how many atoms we see. So we thought we improve a few things, and then yes, also rotations between the spin states should also and possibly also if we find the right type of momentum pulse could also be interesting because they are also correlated in momentum.
Can you explain again what's the advantage of using the cavity compared to the, let's say it's typical standards?
Yeah.
0 creates a plus minus 1.
It's time, speed.
Speed because it creates it in a predefined mode, momentum mode.
And in a predefined mode, yes, it's those two things. It's a predefined momentum mode. So if you think of interferometer, that is nice.
Or you could
and in the other, you would have to filter out, yes. And the other one is also typically 100 milliseconds. So it's 3 orders of magnitude slower. So this is
faster.
This is much faster. So we will follow up.
So thank you for a very nice talk. I have a question about the first part of your talk when you discuss the swap gate. So it seems like your initial state preparation is not perfect, and increasing initial state preparation seems that it can boost your fidelity by a lot. Do you understand well, and do you know how you can improve your?
There are a few things that not all atoms are prepared in pairs, so one would have to find a cleaning mechanism, which is possible. And then there are also, if we go, in particular, since we have harmonic traps at the outside, there are low density regions with small number of pairs, so one could separate them. Of course, well, there are some limitations experimentally of what we can see at the moment, but kind of the fundamental ingredients, they are very promising, I would say.
Thank you.
Yeah, Christian.
I have a question to the first part as well. So another problem, I guess, sort of with this quantum computing in mind, is timescales. So your transport is on the
the transport. Yes, but you always, I mean, the lowest time scale is always the bottleneck. And at the moment in these Rydberg quantum computers is the measuring time scales to measure where there's an atom, and that is also millisecond time scale. So And what I like about that type of interaction is that here the atoms are really controlled in the external and in the internal and the external degree of freedom. And then the interactions, since they are in the ground state, there is only the overall magnetic field they would be sensitive in their interaction, and not some laser pulse that how well the Rydberg state is made. So I would, that doesn't make me too nervous. But of course, it's not as fast as superconducting qubits. But they cannot connect this with this and that and that. So I think it's it's fun to follow up on that.
Philip?
So in this last part, you mentioned you wanted to basically turn S-wave pairs into P-wave pairs with this.
Yeah, that would be nice. Yes.
I didn't see that yet. Like, I mean, this EIT scheme couples to the internal degrees of freedom, right? But you want to actually couple to the relative wave function of the pairs to.
Yes, they are exactly to do a phase shift on one of the pairs and not on the other pair, and this EIT acts on one of the pairs.
One of the atoms.
One of the atoms. Yes. Yeah. That would be the ideal. No, not that I say that it's all worked out precisely because we wanted to see is there any chance. But at least
Don't you need like a spatially varying coupling for that to actually couple to the relative wave function?
Yeah, but you could do that also in ripples and. Yeah. It's a mild yes. Yeah. So there might be detailed problems, but the basic idea is that.
Question? I have another question. When you're tuning to this very special point in the first part again, when you transport through
yes,
it,
yes,
doesn't matter so much you can.
Yes, yes.
Of course, it's interesting to ask if you don't do that, then of course you're starting to entangle.
Yes, yes.
The system.
Yeah.
What kind of entanglement you create? You create something interesting. Can you maybe detect that because you are in a massively parallel?
Yeah. Yeah, yes, there we need help to understand these things. Yes, we don't know. Of course, at the very beginning of my first measurement, we did this massive entanglement, but we could not read it out. We just had these different peaks, and then we thought, oh, let's get some structure into it, and then we figured out we can actually get structure into it. But I agree. It's one may be able to create extremely interesting states, but we do not know at this point.
Questions? I have a quick one on the cavity induced pairs. So you had this earlier work where you basically looked at the super solid, for example, or the
yes.
The difference between this new work and that. First of all, that's of course a transient, but eventually it should also. It's a similar type of process, but it's a spinful.
Yes. Yeah, no, this is, I thought about that a lot because where is the difference? Yes. So there are two differences. Of course, one is a time scale and that we at this point avoid losing any photon. Okay. But also it is a running wave. And the running wave, another way how to look at this is we pump with the running wave and then we create this pair. And now let's look at the atom system. Mm-hmm. The fact that we don't lose a photon means we don't know the phase of the field that we had in the cavity. And if you look spatially now, on our cloud, we have a spin pattern. But it's a correlation pattern. So we don't know whether it sits here or a bit shifted. And in the super solid there, if it goes into this Z2 breaking, then it sits either here or there. Here, ideally, as long as we haven't lost the photon, it sits both here and there.
Mm-hmm. That's okay. Nice. Good. If there are no more questions, I think let's thank Tilman again.
Thank you.
I mean,